Welcome to the course on scalable data science. My name is Anirban. I'm from IT Gandhinagar. Today's topic is going to be on random projections. So before we start talking about random projections, let us take a look at this phenomena called the curse of dimensionality. Since you're taking the course, I don't need to sell the concept of large data to you. Or even the concept that data is not only large, most of the data that we collect has a very high dimensionality, right? So imagine, for instance, that you are creating a classifier for individual web pages or for individual documents, right? So the first task at hand would be to represent a document or a web page as a vector. And this vector then is inherently very high dimensional. For instance, one trivial way this vector you could obtain this vector is just by taking, let's say, the English dictionary and then seeing which words are in the document or not. So the representation of a document is then this binary vector, for instance, right, whose dimension equals the number of words in, let's say, the English dictionary, right, which itself is pretty large. And if it's a web page, for instance, you might need to add in HTML tokens, you might need to add in bigrams or trigrams, which are basically tuples or pairs or tuples or k-tuples of words, of consecutive words. Okay, so there is no question that most of the data that we face has dimensions that we don't really have much intuition about. For instance, the problem is that when data becomes high dimensional, a lot of the intuition that we bring from low dimensional sort of pictures or images or intuitions completely break down, right? And let's see one simple example of this, right? So imagine that you're generating data from a normal distribution, okay? So if it was one dimensional, then you could easily draw a sort of a picture of this, which is the standard bell curve, right? So which says that this would be the bell curve in one dimension, okay? And if you look at this, you can easily see that most of the data is very concentrated around the center, mu, okay? Most of the data lies very close to mu, right? But now imagine that you are generating data not in one dimension, but in some dimension d, right? So what you're generating, so what you start with is a center mu that is a point in Rd. So think of d as something pretty large, right? But it will turn out that we'll see this, the non-intuitive phenomena that we're talking about, even for pretty small d, even for d equal to 10, 20, etc. Okay. So now we are generating d-dimensional vectors, okay, and we are generating them as per the following distribution. So each entry, let's say the ith entry xi, is nothing but a normal variable whose center is mu I, which is the ith coordinate of the center mu, and whose variance is 1, okay? And the xi's are independent of each other, okay? So one way to sort of write this distribution is to say that x comes from a multivariate normal distribution, right? So the center of this multivariate normal distribution is this vector or the point mu, which is a d-dimensional vector, and the covariance matrix of this happens to be ID, right? Because the variance of each of the coordinates was 1 and the covariance of two different coordinates is 0. Therefore, the entire covariance matrix turns out to be the identity matrix. So now the question is that if you look at this d-dimensional space, right, do most of the data points lie very close to mu or not? Right, because that was what the intuition that we took from the one-dimensional case, that most of the data points in the one-dimensional case was very close to mu, right? And if you want to calculate this, if you want to sort of see an intuition for this, right, we need to let us try to calculate this, the distance x minus mu square, right? So for a let's say x is a sample from this distribution, and I want to see how does this random variable behave, this x minus mu square, right? So this, you can imagine, is then the random variable that captures the distance between the data point generated according to this distribution and the mu, right? So if most data points are close to mu, this particular random variable that we wrote, the x minus mu square, right, should be pretty small, right, if x is more or less always close to mu. But is that the case? So to see this, let us try to calculate the expectation of this random variable. Okay, so this is a scalar quantity, of course, because it's a distance. So now, because x is a multivariate normal distribution whose center is mu, x minus mu is also a multivariate normal distribution whose center is 0, and the covariance matrix remains the same, right? So the center is 0, the covariance matrix is ID, which means that if I write this down. So I have just used the definition of the L2 norm. So the L2 norm between x and mu, the square of that is nothing but the sum over all I equal 1 to d xi minus mu I square, right? And because xi minus mu I, by the definition that we have given out here, xi minus mu I again is a random variable, now with expectation 0 and with variance 1. Therefore, this is nothing but the sum of the variances, right, which is d, because each of them has variance 1, right? So what that means is that, and it's not very hard to show, that not only is the expectation d, right, the random variable x minus mu square is actually pretty close to its expectation, which means that what we'll see is that x minus mu 2 norm will be more or less square root d plus lower order terms, order small o of square root d. Okay, so here we got d because we were taking the square of the distance, and when we do away with the square, we get a square root d, right? So what does this statement mean? That the x minus that for most of the data points, which means that with high probability over the choice of x, right, x minus mu 2 norm of that will be more or less square root d plus small o of square root d. What does that mean geometrically? Geometrically, what it means is that if you look at the ball of radius d around mu, right, most of the data points will be on the surface of this ball, right, and on a very small annulus around it, and the width of the annulus is small o of square root d. It's actually something like d to the 1/4 or something. Okay, so this is already pretty counterintuitive, right? Because most of the ball is hollow. If you imagine that most of the ball is mu lies at the center of the ball, most of the ball is hollow, and almost all the data points lie on something that's very close to the surface of the ball, right? That is not what we were expecting if when we look at the one-dimensional plane, right? So this is, I mean, and phenomena like this are fairly common. Right? So the point that I'm trying to make here is that dealing with high dimension is a non-trivial thing, and it is not just a question of our intuitions breaking down. There are a number of other issues. For instance, if you are trying to build a model, for instance, right, and the number of features is something that's close to the number of examples that you have, then your model is bound to overfit unless you very strongly regularize, right? So, and one method of regularization is essentially cutting down the number of dimensions, and this is what we'll try to do, right? So our basic intuition that we'll follow is that if the number of dimensions is too large for me to handle, and we have to learn a model or solve an optimization problem which depends on the number of dimensions, then one of the very common tricks in machine learning is to reduce the number of dimensions to a manageable quantity, something like k we'll typically call it k, which is going to be much less than the number of original dimensions that we're presented with, and then we'll work with the data that's of dimension k. Okay, and this theme will comes over and over and over back again in machine learning, right? For instance, this is also, and this is known by various names. It's known as finding out the intrinsic dimensionality of the data, being able to do feature selection effectively, and so on and so forth. Right? And depending on the particular variant that you're interested in, there are different ways of actually formalizing how to do this reduction. Yeah, you have seen singular value decomposition before, or principal component analysis before. That's one way of doing this. You've also seen you might have also seen factor analysis before, or independent component analysis, or feature selection. These are all different formalizations of the same theme, that we want to reduce the number of dimensions and of the data. Okay. So random projection is a unique one among them, and it's unique in the sense that it is possibly the only one that's data oblivious. So we'll have two properties. Number one is that we'll have we'll make the dimension reduction data oblivious in some sense. That is, how we do the dimension reduction is completely oblivious to the data set that we presented with. And secondly, we will make sure that we have very nice, very tight, interesting guarantees on what we can say are on the structure of the original data versus the structure of the reduced data. Okay, so what is this guarantee? This guarantee is going to be as follows: that suppose we have points x1, x2, xn in Rd, which are Euclidean space, and suppose I want a representation of these points as x1 prime, x2 prime, xn prime, where xi prime is the representation of the point xi, and they should lie in some dimensional space Rk. Because I started with the Euclidean distance, let's say we also want to preserve, we also want the distance function of this target space to be also Euclidean, and we also want k to be much smaller than d. Okay, so the kind of guarantee that we want is that the distance between xi and xj, right, should be more or less equal to the distance between xi prime and xj prime, and this should ideally hold for every pair. Okay, what it means is that imagine that you started with a kind of tetrahedron in space, right, and you want to reduce it to a much smaller number of dimensions, right? And you want to make sure that the distance between all the points are preserved. Right, now it's easy it's not too hard for you to see that if you start with a tetrahedron in 3 dimension and you want to reduce it to 2 dimension, right, and want to preserve the exact distances, that's not possible, right, because you have to squish something or the other, right? So this preservation can only be done approximately. So what is this notion of approximation, and how does that help? So very interestingly, something like this is fairly easy to do in a particular sense, right? And this was found by, and this construction originally came from two mathematicians, William Johnson and Jerome Lindenstrass, in this lemma that they gave. It's still called a lemma, in about 1984. Okay, what it says is that such a construction, not only does such a construction exist, you can actually find a linear mapping that achieves this. Linear mapping is the same as a matrix, right? So what it says is that suppose you are you fix two parameters. Let's say at this point, let's forget the delta. Let's fix a parameter epsilon. So think of epsilon as my error tolerance, as in how approximately do I want to maintain the original distances. Suppose epsilon is something greater than 0, and you start with a k which is going to be, remember, k is going to be my size of the target, my target dimension. So k should at least be something like c by epsilon square log n. We'll decode slowly how that came about. The result by Johnson and Lindenstrass says is that there exists a linear mapping A such that for all pairs ij, right, for all pairs ij, the distance, the L2 distance between axi and axj lies within a 1 plus minus epsilon guarantee, the 1 plus minus epsilon factor of the L2 distance between xi and original xi and xj. So supposing this was the original distance xi minus xj. This is the value of this. This is the real line. So the distance between axi and axj, right? And this is 1 minus epsilon xi minus xj, and this is 1 plus epsilon xi minus xj, right? So what it says is that the distance between axi and axj, the projected points, lies in this interval, and this happens for all pairs ij. Okay. So we can actually show that if I choose this linear mapping, it's possible to choose this mapping A in a random manner such that this actually happens with a high probability. So what that means is that not only does there exist such a mapping, it's also easy to find such a mapping, right? Because once we give a random construction for it, for specific types of random construction that we'll see, right, that we will be able to guarantee that this particular property holds with very high probability. Okay, so this will give a randomized algorithm for this particular problem, for this particular matrix construction. Okay, so the constant c that you see up here that I had forgotten to write is in practice fairly small. Right? It's something like 6 or 7 is what you need to prove in theorems, and in practice it comes out to be smaller than that. So just to sort of harp a little bit on the intuition of this problem, why are we interested about pairwise distances? Right? So this is the picture, right? That we start with, let's say 1, 2, 3, 4, 5, or even more dimensions in my original space. So this is my original space, and these are the points. These blue are the points, right? For any of these points x, we multiply x by a, right? And then we look at, so this is the image of the point a, x, right? And this target dimension a, this target dimension k, is much smaller than is potentially much smaller than the dimension of the original space, right? In fact, it only depends on the error epsilon and on the number of points that you're interested in, right? It does not depend on the original dimension, right? What it says is that if you look at all the pairwise distances here, they are more or less maintained in my target dimension up to this factor of 1 plus minus epsilon. Actually, maybe it should have been this point. Okay, so why is this important? This is important if, for instance, you imagine that the original points were clustered in some way. Then preserving the pairwise distances also implies that you're preserving the cluster structure. Similarly, if the original points are separable, right? For instance, we have class 1 and we have class 2, and they happen to be nicely separated from each other by some hyperplane, right? Then preserving the pairwise distances also means that the resulting problem is also separable, which means that I can actually learn a classifier on this target dimension very easily. Okay, so the important point I want you to note is that the input dimension does not come into the bound at all, right? Only the number of pairs that we want to preserve or the number of points whose distance we want to preserve comes into the picture, and we'll see why I'm talking about pairs, right? So if there are n choose 2 pairs, right, then it should be log of n choose 2, which is basically the same as 2 log n, right? That should come into my target dimension. And of course there's the 1 over epsilon square factor, where epsilon is the error parameter. So why is it useful? As I've already hinted that it's potentially one of its use, and we'll see very concretely a sort of example later in the course, is that it will help us learn classifiers very efficiently, right? That instead of learning classifiers in my original dimension, very high dimension, we'll do a projection and then we'll learn the classifiers in this resulting dimension. We'll also see a lot of examples in what is now known as randomized numerical linear algebra, right? And here, for instance, we have a huge data set in which, for instance, we want to do matrix factorization. Why? Because maybe we want to build a recommender system. We want to solve a regression problem. And in all of this, a standard trick would be to reduce the target dimension, solve the problem there, and thereby get an approximate solution in the original space with high confidence. Okay, so Now if you go back, we have seen a lot of streaming algorithms. We have seen count min sketch, we have seen count sketch, and so on and so forth. If you go back and think about this, you will see that a number of these are essentially random projections. Right? You've also seen a bunch of algorithms for locality sensitive hashing. Right? And we've also discussed things, variations of KD tree or RP trees and so on. And a lot of these, as we'll see today also in today's class and in next class, a lot of these, again, the core idea behind that is this distance preservation notion. And then we are doing things on top of it. Right? There's a huge literature in communications as well as in computer science called compress sensing. The idea there is that suppose we have a signal and we cannot observe the signal directly, but we can observe it through its interaction, through some interaction matrix. That is, given the signal x, we cannot observe x directly, but we can make observations of the form p times x, where p is called the observation matrix, right? And we might have assumptions that say that, okay, x is sparse, right? And now the problem is that given a y, so x potentially is very, very large dimension, but is sparse, small number of non-zeros. By making a small number of observations y, which is ideally only proportional to the number of non-zeros of x, right? We want to reconstruct x, right? So the number of observations should be a function of more the number of non-zeros of x than the dimensionality of x. Okay, this is the compress sensing literature, and there's very intimate connection between compress sensing and random projections. Okay, so we talked a lot about why this is potentially useful. But how do we create such a matrix? Okay. So here is a very easy way of creating a matrix. A bunch of such algorithms have been given by researchers. We'll look at an easy way about which we can actually prove that it works. So the way we'll create the matrix is imagine that we start with an empty matrix which is of size k by d, and we're going to fill this up. So how do we fill this up? It's very simple. You go to the entry ijth entry, and for filling up the ijth entry, you sample a random variable from n01, basically from the standard Gaussian. You take that value and you set that as the value rij, and you keep on doing this for all the entries. So independently, you sample k times d entries, and you use that to fill up the matrix. That's it. Okay. So this is my random projection matrix. Okay. And so one other thing we need to do is that we need to normalize it by this factor 1 over square root k, and we'll see, and it's easy to see why. Right. So if you notice what the expected norm of a row is, so take the first row, right? Each of these are samples from n01, and therefore each of them have variance 1, which means that expectation of xi square, where xi is the ith entry of row, is 1, and therefore the expected norm, the first row norm, is equal to k, right? And I want it to be 1, right? Because if it is going to act as a projection matrix, right? If it is going to act as a projection matrix, I need it. Basically, if it is going to act as a norm preservation matrix, I need the norm of each column to be 1, not the row. Maybe I was talking about a row before. So I need the norm of each column to be 1, right? So therefore, I'm dividing by 1 over square root k. Okay, so why does this work? In order to see why this works, we need to prove a smaller result first, and this is really the core of the theorem, right? And this is called the JL lemma. Okay, so what does this say? What it says is that suppose we set k to be some at least c by epsilon square log 1 over delta, where epsilon and delta are two non-negative quantities. Then for the previous matrix that I created, let me call that A, and let's take any vector x that has two norm 1. Then Ax, the probability that Ax lies in the interval 1 minus epsilon and 1 plus epsilon. So the two norm Ax lies in the probability that the two norm of Ax lies in the interval 1 minus epsilon to 1 plus epsilon is at least 1 minus delta. Okay, so see, notice a couple of things. First of all, I'm stating the theorem only for the two norm of x equal to 1. And this is enough because this is a linear mapping. because for any other x, I can always normalize it by that norm of x, right? And once I multiply by a, I can again multiply back by the norm and so on. So just stating the theorem for the unit norm vectors is enough, right? And also notice that if I can actually show this, particular lemma, right, then in order to show the previous Johnson-Lindenstrauss theorem, we needed to look at all pairs xi minus xj, right? And there are n choose 2 pairs, so I needed to take union bound over all these pairs and I would be done. Okay. So what we'll do in this in this lecture is just see the proof of this and then finish. Okay. So why does this work? Let's just do a proof sketch, a brief proof sketch of this. That suppose we look at the vector ax, right? And the vector ax is nothing but 1 over square root k rx, which is nothing but 1 over square root k. Let me call the entries, this is a k dimensional vector y1 to yk, and yi is summation j ri xj. Okay, so this is the definition of yi. So what we are interested in is the 2 norm of ax square, which is 1 by k summation I yi square, and we are interested in the distribution of this. So the thing that comes to our rescue is something known as the 2 stability of the normal distribution, which is as follows: that if p and q are 2 normal random variables and p happens to be from n mu sigma, right, that is the mean is mu and the standard deviation is sigma. Q happens to be from n alpha gamma, the mean is alpha and the standard deviation is gamma. Then p plus q has mean alpha plus mu plus alpha, the sum of the means, and the variance is sigma square plus gamma square, which means standard deviation is square root of that, and furthermore it is a normal distribution. It's a normally distributed random variable with this particular mean and variance. Okay, so this is what we'll use. So now it's easy to see that each yi is really the sum of normal random variables, because rij is a normal random variables, therefore rij times xj is a normal random variable, and therefore yi is also itself a normal random variable with the expectation to be the sum of the expectation and the variance to be the sum of the variances of this. It takes only a little bit of calculation to see that the variance of summation rij xj is really summation of a j xj square, which is equal to 1, because I started with xj to be norm 1. Okay, so therefore each yi is really distributed as n01, right? And now therefore the expectation of this quantity 1 by k summation yj yi square, which I was defining to be z, is also 1. Furthermore, I can also say that k times z is something known as a chi-square distribution with k degrees of freedom, right? Because the square of a normal distribution is a chi-square distribution. And beyond this, we just need to apply chain of bounds. We want to show that probability of z bigger than 1 plus epsilon is small. We apply the standard steps that we did in sort of showing chain of bounds, and it's again really a chain of style bound, but it's a little more complicated because it involves the moment generating function of the chi-square distribution and some algebra to show that the probability that z is bigger than 1 plus epsilon is at most x puff minus k epsilon square c. Okay. So that's it really. I mean, and the proof for the lower tail bound is also the same. In next lecture we'll discuss some other properties of the random projections. Okay, and thank you.